to talk. Hardy-Weinberg equilibrium is a measure of evolutionary change. And so there were two guys, Hardy, who was a mathematician, and Weinberg, who was a physician, that actually came up with this idea. And so really it's a mathematical model that will predict the alleles in a population. And so really this model is good for measuring if there are evolutionary forces acting on a population, or determining if a population is evolving. So you can, using what you know about a population, you can determine what the allele frequencies will be. And then over time, you can collect those allele frequencies again on your population, and then you can use that to determine if mathematically your population is evolving. And so the important thing about Hardy-Weinberg is that it assumes that your population is not going to evolve. It's kind of like your null hypothesis we use in the chi-squared. And so if you look through the beginning of the PowerPoint, you'll see those 5 items that act on populations and that help drive evolution. And so Hardy-Weinberg is assuming that none of those things are happening. So it's assuming that you don't have selection happening, so no natural selection is acting on a population. There is no mutation occurring, so no random mutation at all. Individuals are not leaving, or no new individuals are coming into the population, so there's no immigration or immigration. The population is not going to get small through like a bottleneck or some type of weird thing happening, so the population will remain large. And then the last thing is that the mating will be random. So there's no selection in mating, all, just round them up and randomly mate. And so that's the assumption of Hardy-Weinberg equilibrium. And those assumptions have to be true in order for a population to not evolve. So we are going to use a cat population to kind of model this Hardy-Weinberg equilibrium. And so in this cat population, we have 2 alleles that determine hair color or fur color, and that's white or black. So capital B is the dominant allele that will give you black hair, and then lowercase b's are recessive, and that will give a cat white hair. So Hardy-Weinberg actually has 2 formulas. And so the first formula deals with alleles, okay? And so in our cat population, we know we have 2 alleles. We have capital B and we have lowercase b. And so in the Hardy-Weinberg formula, P will stand for capital B and Q will stand for lowercase b. So P is always going to be your dominant allele. Q is always going to be your recessive allele. So that is one of the Hardy-Weinberg formulas. The other Hardy-Weinberg formula accounts for the individuals in the population. And so we know that with 2 alleles, you can have 3 different combinations. You can be, homozygous dominant, homozygous recessive, or heterozygous. And so P squared, or 2 big B's, homozygous dominant, is going to stand for P squared. PQ will be your heterozygous individuals, and Q squared will be your homozygous recessive. And kind of a good way to think about this and to remember this is if you take PQ times PQ and you put it into a Punnett square. Okay? And so if you put a P and a Q and a P and a Q, you're going to get 2 P's, a P and a Q, a P and a Q, and 2 Q's. So there's your P squared, there's your Q squared, and then here is your 2 PQ. So just kind of another way to remember that, that formula stands for individuals, and then the top one stands for alleles. And then this is just kind of a repeat of that last slide, just that P times P is P squared, Q times Q is Q squared, and then 2P times Q gives you 2PQ. And now both of these equations add up to 1 or 100%. And so that makes sense, right? If you take all the homozygous dominant individuals, all the heterozygous individuals, and all the homozygous recessive individuals in your population, that should equal 100% of your individuals. Or if you take all the P's and all the Q's of your population, that should add up to 100%. All right, so let's do a little practice, okay? So now, sometimes you might just need to use one equation. Sometimes you're going to need to use both equations. So it's just always a good idea to write both equations somewhere or have them close so that you have that information with you. And so in this example, the frequency of B in a gene pool is 0.9, okay? We know that capital B actually stands for P in our Hardy-Weinberg problem. And then lowercase b is equal to 0.1. In this case, that is Q. And so we want to figure out from this information we have what percent of the population is big B, what percent is big B or little b, and what is big B, little b. And so from our previous slide, we know that if we know what P and Q are, then we can just plug it in to this equation and we'll be able to figure out the percentage of each of those genotypes. And so big B is P squared, okay? And so if we take 0.9 and we square that number, that is going to give us 0.81 or 81%. So that means that 0.81 or 81% of our individuals is going to be big B. Okay, so next, let's do 2PQ. That'll be our heterozygous individuals. So if we take 2 times P, which is 0.9, times Q, which is 0.1, we get 0.18 or 18%. And then that is equal to our heterozygous individuals. And then finally, we can take Q squared, which would be 0.1. And then we would get 0.01, which is which equals 0.1 or 1%, and that would be little b. And so then now, if we take 81 plus 18 plus 1 and we add those all together, we should get 100%, and then that's just a good way to check your math. So 1% of the individuals are homozygous recessive, 18% are heterozygous, and 81% are homozygous dominant. All right, so another way that these problems work sometime is that most often, you're not going to just be given the frequencies. You're just going to be given information about the population. And so here we have just some information about the population of cats. And so again, it's always good to write both equations so that you have them both ready to go. And so given this population of cats, we want to know how many of each genotype, okay? And so really, you have 100 cats, 16 of them are white, okay? And we know that white cats have to be little b. So we know that 16 out of 100, or 16%, of our cats represent that homozygous recessive genotype. What we don't know, though, are these 84 black cats. And the reason why is because they can be big B, or big B, little b. And so what we need to do is we need to use our equations to figure out how many are going to be big B, and how many are going to be big B, little b. And so what we're going to do is we're going to use the information we have to figure out P. And so what we know here, what we know right now, is little b, okay? So little b, or Q squared, is equal to 16%, or 0.16. And so what we can do is we can figure out from that information what Q is by itself. And so in order to find out Q, we would need to take the square root of both sides of that equation, and we would get 0.04. So now that we know what Q is by itself, we can plug it in to this equation up here. And so if we take 1 minus, sorry, and that shouldn't be 0.04, that should be 0.4. If we take 1 minus 0.4, we would get P to equal 0.6. And so now that we know what P is, we can use this P value and plug it in to these up here. So now if we take P squared, or 0.6 squared, we're going to get 0.36, or 36%, will be equal to our big B genotype. And then if we do 2PQ, or 2 times 0.6 times 0.4, we should be able to get our value for our heterozygotes, which is 0.48, or 48%, will be big B, little b. Okay, so hopefully by doing those two equations, that'll help to kind of introduce you to the Hardy-Weinberg problems and make you able to do those on your own. And then let's talk about like how we use the Hardy-Weinberg equation. So if we look at this cat population that we just figured out, where 36% are homozygous dominant, 48% are heterozygous, and 16% are homozygous recessive. Over time, we can look at how this population changes to determine, is this cat population Hardy-Weinberg equilibrium? And so if this population is not evolving, we would assume that every single one of these numbers is going to stay the same. And so let's say after some time, we look at this cat population again, and we determine that these are our new allelic frequencies. So we have 0.74 P squared, 0.10 2PQ, and 0.16 for Q squared. So this stayed the same, right? These two stayed the same. This went down, this went up. And so based on this information, we can tell that something is changing in this population. And for whatever reason, the heterozygote condition is not favorable in some way. And who knows exactly why that would be the case, but that could be something that an evolutionary biologist would study. Okay, so let's say, again, we take some sample data sometime later, and then we find out that these are the new frequencies. And so now, instead of P squared going up, it's gone down, and 2PQ has actually gone up from that 0.48%. And so that would tell us, that there's some type of heterozygote advantage here. And for whatever reason, the heterozygote cats are faring better than our homozygous dominant cats here. And so that's kind of how you use Hardy-Weinberg equilibrium to determine if a population is changing or not.